All right, we have just a little bit to finish up. It actually might not even take us the whole time today. We'll see. All right, so last time we were talking about partial orders. Okay, who remembers? If it's a partial order, what are the three characteristics that it has to have? Yeah?
Reflexive, antisymmetric, transitive.
Good. They just rolled off your tongue. Good. Good. So reflexive, antisymmetric, transitive, that makes it a partial order. Okay, and we also talked about some partial orders that are very special because everything can be ordered, not just some things, and that's called a total order. Okay. And we also looked at Hasse diagrams that represent these, and they're essentially the same information that's in a directed graph, except that we try to minimize the information so that the number of edges doesn't get overwhelming, and it's a lot easier to look at the Hasse diagrams and get an idea of what the relationship is. So these three examples, we're going to change directed graphs for partial orders into a Hasse diagram. Okay. So we know that in a Hasse diagram, there's not going to ever be any self-loops. So all of these things will get eliminated, okay, in our Hasse diagram. Okay. We also know that in a Hasse diagram, any minimal elements need to be at the bottom, any maximal elements need to be at the top. So if we're trying to convert a digraph into a Hasse diagram, it's a good idea to just, see if there are any minimal and any maximal elements to give you a starting position. Okay, so are there any minimal elements in this graph? Just kind of ignore the self loops. Remember, minimal would mean that there's only things going out and not things that are coming in. So only arrows going out. So are there any things in this graph that have only things that are going out and not things coming in? One. Yeah, it's got an out arrow, like all 4 out arrows, no in arrows once we eliminate the self loop at least. Okay, so 1 and then 6. Are there any maximal elements that has arrows coming in but never anything going out? 4 and 6. Okay, so if we can identify those, that'll help us to quickly draw the Hasse diagram. We know that 1 is a minimal element. It's going to have to be lower than everything else in the diagram. Okay, so from 1, okay, it goes out to everything, 1, 4, 6, and 3. Okay, we know 4 and 6 are pretty high up, so let's just consider 2 and 3 next. All right, so 2, we know that 1 goes to 2. Okay. 1 also goes to 4. So we've included this edge. So we only need to include the edge from 1 to 4 if we can't get to it any other way. Well, 2 goes to 4, and then we have 1 to 4. That's like a transitivity edge, right? 1 goes to 2, 2 goes to 4. And then because of the transitivity property, 1 goes to 4 as well. But if we added 2 to 4 in here, actually there's no arrows. We don't need an arrow in this. Okay. Then we automatically have an upward path from 1 to 4. We don't really need this edge. Okay, we just need these 2 edges. If we go over now and look at 3, okay, 1 goes to 3. We should put that one in. So that takes care of that one. But we don't really need this 1 to 6 because we have 3 to 6. If we put 3 to 6 there, okay, this again is just that transitivity edge. That one's not important because I get that upward path from 1 to 6 this direction. Okay. So the only one I've taken care of that one. The only one I haven't really accounted for is this 2 to 6. Okay, so is that, we have to look at what we have right now. Can that be implied from what we have here, or are we going to actually have to add that edge in there? Okay. Well, there is no upward path currently from 2 to 6. Like the only way for me to get to 2 to 6 would be go down and then go back up. That's not an upward path though. Okay, so you never go down, you only have to go upward. There is no upward path, so we're going to have to put that 2 to 6 in there to account for that relationship from 2 to 6. All right. That takes care of every edge in that directed graph. So the Hasse diagram we have is there. 4 and 6 are maximal elements, 1 is a minimal element. We have all the relationships in there, so it should be good. Okay. All right, let's go through the similar process for this one. Okay. Again, let's eliminate all the self loops. We know that those aren't going to be in there. Are there any minimal elements in this one? The arrows are a little blurry. Let me add them in there a little bit bigger so you can see them. A is a minimal. Because A only has arrows going out, nothing coming in once we eliminate the self loop. How about any maximals? C and D. Okay. So that should be super helpful in at least a start point of A. Okay. Well, we know A is going to have to go to C. That's really the, I'll put that one like here. Okay, that takes care of this one. A goes to B, and A can get to D through B. So we would put B over here. That takes care of this edge. We'll put the BD edge in here. Okay, that takes care of this one. And this one is here because of transitivity, but at this upward path that I have from A to D implies this one, so I don't really need this edge. I'm not going to include that one. So I've considered everything there. I have, when I look at my diagram, I have a minimal element of A and 2 maximals of C and D, nothing above them. All of my relationships are accounted for. Okay. On this last one, again, we'll eliminate all the little self loops. Do we have a minimal element? The arrows are here, 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 and here. It's blurry. This one is a minimal. It's labeled with a 1. Okay, so it's got an arrow going out, 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 nothing coming in. Okay. 2's got stuff in and out. 3's got stuff in and out. 4, however, in, everything is in. So 4 is a maximal. Okay. So 1's going to be on the bottom. And hopefully it's pretty obvious looking at this one that we've got this path that goes from 1 to 2 to 3 to 4 straight up here. Okay. And so all of these other ones that are in here are all because of transitivity. Those can all be implied by the straight upward paths that I have from 1 to 2, 1 to 3, 1 to 4, 2 to 4. All of these ones are already implied. So all of these are partial orders, but this one is special. This one is what? A total order. Yeah. Okay. So that's creating a Hasse diagram from a directed graph. We also might want to be able to draw a Hasse diagram from just a list of ordered pairs that describe the relation. Okay, so definitely a Hasse diagram is way easier to make sense of than just a list of ordered pairs, right? So if we know that this is a partial order, we know we can eliminate like all the self loops. None of those are going to have to show up. So this AA, BB, CC, D, all of these ones that are here because of the reflexive property, none of those have to show up in my Hasse diagram. That's always implied. So I won't have to really include edges for any of these in my Hasse diagram. Okay. So finding mins and maxes is a little bit trickier in here. Okay. But mins, okay, so think about we would have a directed edge from B out to E. So we would have something coming out of B here, something coming out of B, out of C, out of C, out of A. Okay. And then Here we would have something coming into E, into D, into A, into F, into F. Okay. So to find a min, are there any of these where there's only things coming out and never anything coming in? B and C. Okay, so B has stuff coming out, and you look, B never appears in the second position of an ordered pair. It doesn't have anything coming in. C has stuff coming out, but if you look at the second position, there's never a C there, never anything coming in. Okay. A maximum, is there anything that only ever occurs in the second position and never in the first? F and E. Okay, yeah, so E here never appears in the first position. F here appears in the second, but never appears in the first. Okay. Sorry, what? And D, okay, D only appears in the second position as well. Okay, and never in the first. So D never appears there. Okay. So that should be helpful in getting us started. Okay, so we know that we probably want our B as a minimum, and we want C as a minimum. So let's start at B. Okay, so we would have to have an edge from B to E. Okay, so that takes care of this one. Okay, we would have to, and let's look, let's follow that path up. Okay, are we going to come from E to anything else? Well, no, we said E is a maximum. So that's kind of the end of that path. Okay, from B, we're also going to have to go out to D. So that takes care of that one. Okay, and then can we follow this path? Do we go from, are any of these D? No. Okay, so we don't have to worry about continuing up that branch at all. Then from C goes out to A, so we'll put that one in. Okay, and then let's see if we need to follow that path along. Okay, so C went out to A, then A goes to F. So we'll put that one in. Okay, that takes care of that one. And now, do we need a CF path? Well, or edge? Well, no, we already have an upward path from C to F, so that's already implied, so we don't need to add an edge for that one, but at least we've considered it and we have that in there. Okay, so we've now covered everything. All of these ones are implied from reflexivity. This one is implied by transitivity. Okay, and so we've included only the important edges, and we should match it up. Yeah, B and C are minimal, F, E, and D are maximal. Everything that we expected is in our diagram, so it looks like it's good. All right, so that is our partial orders. Okay. The next thing that we want to look at is another special kind of relation called an equivalence relation. So, like partial orders, equivalence relations are reflexive and transitive. The thing that's different is that they're also symmetric. Okay, so equivalence relations are reflexive, symmetric, transitive. So for partial orders, you remember we use a special symbol. Oh, it was on my other sheet. It looks, remember for partial orders, I don't want to defile this one, but it looks like that, right? That's the symbol we use for partial order. Kind of looks like a less than, but we make it curvy to show that it's a general relationship that's not specifically less than, it just acts like less than. Okay, so for an equivalence relation, the general symbol that we use is this little tilde. You may have used that to express the similar relationship in geometry, like for similar triangles or similar figures. Okay, and they use it there because similarity is an equivalence relation. And okay. All right, so this little symbol, okay, we would read it is equivalent to. Okay, so that's the general symbol that we use for an equivalence relation, one that is reflexive, symmetric, and transitive. Okay. So we're going to look at an example. So let's say we have the set of non-negative integers from 0 to 10. And our relation is going to be defined as x is related to y if x mod 4 and y mod 4 are the same. So mod, hopefully you're familiar with this operator. It's the same as like the percent operator in Python or in C++ or in Java, right? So this, right, means the remainder when x is divided by 4. So you should be thinking the percent operator, right? So maybe as a side note, we'll just list what all these are. So if I had 0 mod 4 and 1 mod 4 and 2 mod 4, etc., at least do a few of them. Okay. We'll stop there. Okay, if I do 0 mod 4, that's what remainder would I get when I divide 0 by 4? 0. Okay. If I divide 1 by 4, what remainder would I get? 1. And hopefully you can easily see you'll get 2 and 3. If I divide 4 by 4, what remainder? 0. If I divide 5 by 4, 1. And then hopefully you see 2 and 3. It's very cyclic in nature. Okay, so if you've ever used this in programming, it's always for these cyclic things like circular arrays and circular print queues and all these things that kind of go in a circular fashion. Okay. Okay, and then, they go on from there and repeat. They'll just go 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Okay. So let's say we were going to draw a digraph for this particular relation. Okay, so let's start with 0. Okay, so of course, 0, we want to find all the things. It's like, what would 0 be related to? Well, 0 will be related to another number. Okay, well, 0 has 0 mod 4. So the things that it will be related to are things that also have, that are 0 mod 4, that have a remainder when divided by 4. So clearly, 0 is related to itself. Okay, has the same remainder as itself when divided by 4. We see that it has the same remainder as 4 divided by 4. Okay. 4 will also be related to 0 if x is related to y is related to x. Clearly this is symmetric. Okay, they have to have the same remainder, so we'd put that in there. 4 is related to itself. Okay. Would 0 be related to anything else? Well, we kind of said that this cycle is going to repeat. So if I put 8 in here, okay, 8's also going to have a remainder of 0. So 0 is going to be related to 8. 8 will be related to 0. Okay, 8's related to itself. And then 8 and 4 have the same remainder. Okay, 8 is related to 0. 0 is related to 4. 8's related to 4. You can see that transitivity in there as well. Okay. So we'll get all of that. Okay. None of the other numbers are related to 0. None of the other numbers are related to 4. None of the other numbers are related to 8, because no other numbers, at least in this group here, have a remainder of 0. So let's go on to 1. Well, 1 has the same remainder as itself, certainly. Also, we see down here it has the same remainder as 5. Those both have a remainder of 1. Those are related to each other. 5 is related to itself. Okay. And then, if we continued this cycle as we said before, we would see that 9 also has a remainder of 1. So 1's going to be related to 9, 9 will be related to 1, 9 will be related to 5, 5 will be related to 9. Of course, 9's related to itself. But none of these are related to anything else. Okay, so we've considered over half of the numbers now, but we haven't gone to 2 yet, so we'll put 2 in there. Well, 2, of course, has to be related to itself. And down here we see it's related to 6. It has the same remainder as 6 did. So we'll get these in here. Okay. And then something else with a remainder of 2. Well, 10 Okay, 10 will have a remainder of 2. So we'll get all of those in there. Okay, so we've considered 0, 1, 2. 3 isn't in here anywhere yet. Of course, related to itself. We see it's related to 7. Okay. And I think that covers everything. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So this is an example of an equivalence relation. Okay. And when you draw a directed graph of an equivalence relation, they're all going to have a sort of similar structure where you get these little disconnected clusters. Okay. So this little cluster, and it's totally connected everywhere in that cluster, and it's not connected to this one over here. So we get no matter what equivalence relation we get, it's going to divide our graph into these little clusters that are disconnected. Okay. So it has these disconnected clusters, I'll call them. Okay. And those disconnected clusters are called equivalence classes. Okay. So an equivalence class is the set, if we take a particular element in our domain, it's the set of all things that are related to that. Okay, so if we went back to this one, okay, this is one equivalence class. So 0, 4, and 8, they all act the same way. As far as this relation is concerned, they're equivalent. They all have a remainder of 0. They all behave the same way. Okay. All of these elements, though, they're different. When I divide them by 4, you get a remainder of 1. But in the sense of dividing by 4 and looking at the remainder, they're all the same. Like, they're equivalent to each other. I always, no matter which one of these I take and divide by 4, I always get a remainder of 1. Okay. And they're different from this. Right? I get a different remainder. These all have the same remainder, so these are all equivalent to each other. As far as the divide by 4 and look at the remainder, I can't tell the difference between 2, 6, and 10. They're all the same. Okay. Because they always give me a remainder of 2. And here with 3 and 7, same thing. I mean, if I went to, bigger a set of integers, I might have more things in there. But I would always, no matter what, even if I had, 100 numbers instead of just 11 numbers, I would still have only these 4 equivalence classes. Okay. Because when I divide by 4, I can only get 0, 1, 2, or 3. Those are my only options. So I'll always get 4 equivalence classes. They might have more numbers in them, but they're just going to be 4 equivalence classes. Okay. All right, so equivalence class. Okay, we take an element, okay, and then we look at every single element that's related to it. Okay, so if I have an x that's related to A, I'm going to stick it in that class. Okay, so the notation for that, I put these little square brackets around an element, okay, and everything that's equivalent to that will be in that equivalence class. So, back to this previous example, okay, how many equivalence classes? We already talked about this. We have a nice little visual picture there. There's 1, 2, 3, 4 equivalence classes. And if we were to write out what they were, well, we just need to kind of pick a representative element from this class. We could pick any of them because they're all equivalent. I think 0 is the most logical one to pick, though, because it helps us get the idea of, oh, the remainder is 0. Okay, so we would have this is an equivalence class. Okay, so that is, if I were to look at it, okay, well, that is defined to be the set of all x that are related to this. Okay, so if I were to think about what's in this class, well, 0 is related to 0, 4 is related to 0, 8 is related to 0. Okay, so these are 2 notations for exactly the same thing. I put 0 with the little brackets around it. That's the equivalence class of 0. All the things equivalent to 0. That's a set of elements, okay, of all the things that behave the same way of 0. Have a remainder of 0 and divided by 4. So that would be this set, 0, 4, 8. So this is just the shorthand notation for it. Okay. And this would also be equal to this, and it would also be equal to this. All of those are the same thing. It's just that this is probably the most convenient name to use for that set. It's short, and when I see the 0, it gives me that idea, remainder of 0 and divided by 4. So, okay. Like, it's not as intuitive with these ones that that's going to be the remainder. So, the next class would be this one. Okay, everything that acts like 1 when I divide it by 4 has a remainder of 1. Okay, so certainly 1 is in that class, but then we also saw that 5 and 9 were in that class. And once again, like I can call it the equivalence class of 5 or the equivalence class of 9. Okay, this is just a nicer name because when I look at that, I see, oh, the remainder of 1 when I divide by 4. Okay, I also can have a remainder of 2. I can also have a remainder of 3. So those would be my other ones. This one was what? 2, 6, and 10. And this is just 3 and 7. And I guess just to be completely out, we could call this 6. We could call it 10. Okay, probably not going to. We could call this one the equivalence class of 7. But these are probably the ones that we would choose to use. So those are the 4 equivalence classes. Each of those represents a set. Okay. Just when you thought we were done with proofs, no, we're not. We're going to do, this is our last proof of the semester, though, probably. There probably won't be any on that. Well, I mean, you'll have to prove that things are reflexive, symmetric, transitive, that kind of thing. But it's not quite like a direct proof or a proof by contradiction or anything. So this is our last proofs of that nature. Okay, so there is a theorem that tells us that 2 equivalence classes are either completely identical or completely disjoint. Okay, so let's say we have an equivalence relation on a set, and there's 2 elements, x and y and a. Then if x and y are related, then their equivalence classes are identical. Okay, so that's either they're identical, okay. Then if they're not related, then their equivalence classes are completely disjoint. There's no overlap. The intersection is the empty set. Okay, so being disjoint means there's no intersection between them. Okay. So we have 2 things to prove. 1, 2, I'll kind of label them there. Okay. And so this is sort of our given, okay, that we've got an equivalence. So let's say let A be an equivalence relation. Oh, no, let R be. They didn't name it. So let R be an equivalence relation on the set A. Okay, and X and Y are arbitrary elements. Okay, so the first thing we want to prove is that if x and y are related, then their equivalence classes are exactly the same thing. Okay, so first we show that if x is related to y, then the equivalence classes are the same. So this one we're going to do a direct proof. Okay, so a direct proof, remember we're going to just assume that this is true and then just show, okay, sort of directly, logically from that this will have to be true. So we're going to assume that x is related to y. Okay, so if we want to show, like, let's just think about the equivalence class of x. Those are all the things that are related to x. So let's just think, oh, well, there's presumably something in that set, even if it's x itself. We know at least x is in there, but there's something in there. Okay, so we'll say and we'll just call it z be an element of A such that x is related to z. Now that might be x. Okay. I'm not forcing it to be x. I'm just getting as an arbitrary element. At least x is in the equivalent class of x. But I'm just going to say a general z. There's some z in the set. X is related to z. Okay. So we have this X is related to Z. Okay. So if we think about the properties of equivalence relations, well, equivalence relations are reflexive, they're symmetric, they're transitive. Since we know that, I guess I should have called this tilde. Okay. Since we know that those three things are there, we should be able to use those to make logical conclusions about them. Okay. So, for instance, if X is related to Z, well, because the relation is symmetric, Z would have to be related to X. Okay. So, because this is symmetric, okay, we know that Z has to be related to X. And now, if we have, notice that we have Z is related to X, and we also have X is related to Y. Well, we also know that because it's an equivalence relation, it's transitive. If Z is related to X and X is related to Y, what can we conclude? Because of transitivity. I think you had it. So Z,
I had it, yeah.
Z is related to X, X is related to Y.
Y is related to Z.
So, well, let's go Z is related to Y. Yeah, Z is related to Y. Okay. Yeah. And then we could get Y related to Z through symmetry, but by transitivity, we're just going to get Z is related. Okay. Okay, so because the relation is transitive, we get Z is related to Y. Okay. And let's do furthermore, like you said, Y is related to Z then, okay, by the symmetric property. Okay. So what we have is that X is related to Z and Y is also related to Z. And Z is just some arbitrary element. So no matter what arbitrary element Z I choose, if it's related to X, it's also related to Y, which means that it's going to always be in X's equivalence class and it's going to be in Y's equivalence class. Okay. So X and Y, so therefore the equivalence class of X has to be exactly the same as the equivalence of Y, because every Z that's in this, okay, since Z in this equivalence class implies that Z is also in that equivalence class. Okay. So for every Z, any arbitrary Z that I pick, if it's related to X, it's also related to Y. Okay. So they are going to be exactly the same. All right, so that takes care of the first one. The second one, we need to show that it's not the case that X is related to Y, then the intersection of those equivalence classes will be the empty set. Okay. Now this one is easiest to do with the proof by contradiction, so that's what we're going to do. So we use a proof by contradiction. Okay. So remember how a proof by contradiction works. Okay. We're going to assume the hypothesis is true. Okay. So we assume that X is not related to Y. And then we're going to say, okay, well, what would happen if the intersection actually wasn't the empty set? Okay. What would and then show that that would produce some kind of contradiction. So let's suppose that the intersection of these two is not the empty set. So if it's not the empty set, there's something in there is a set. So there has to be something. Okay. So then there has to exist some element such that that element is in this set and that element is in this set. Okay. That's the only way that it would. Okay. Oh, I should not, yeah, that's right. So if it's not the empty set, there's some kind of intersection, and let's say, let's just pick an arbitrary element that's in the intersection. So it's in both of these sets. Okay. Well, if Z is in this set, that means that Z is related to X. And if it's in this set, then that means Z is related to Y. Okay. That's the definition of being in that set, is that it's related. Okay. Now, once again, we can use the properties and flip one of these around. Okay, let's say, for instance, let's do this one. Okay. So since this is symmetric, Z is related to Y, so Y must be related to Z. Okay. And now we have this. Y is related to Z. Z is related to X. Okay, so since this is transitive, so Y is related to Z, Z, X, so we get Y to X. Okay. And then X is related to Y by symmetry. Okay. Now, look at that, and look at our assumption. Is there any possible way for us to both have the X and Y are not related and the X and Y are related? Of course not. They can't both be true. Okay, so there's our contradiction. So this contradicts the fact that X is not related to Y. Okay, so we found that contradiction. What does that mean? Well, it means that this thing that we suppose to be true can't possibly be true. Okay. So therefore, it must be the case that actually the intersection between X and Y is indeed the empty set. It takes us back, doesn't it? We love those proofs. Okay. Does all that make sense? Somewhat. You gotta kind of let it sink in a little bit sometimes. Okay. Okay. Well, if you come up with questions, let me know. But I know sometimes it hurts your brain. Okay. The last thing that we need to look at with equivalence classes is this idea of a partition, and this also takes us back down memory lane. Okay, so remember that a partition of a set is a set of non-empty subsets that are pairwise disjoint, and their union is the original set. Okay, so this was way back on exam 1. Okay, seems like such a long time ago, but it wasn't that long ago. Okay, and so equivalence classes give us partitions, and that's why equivalence relations are so important, is they give us ways to partition a set. So if we consider equivalence relation over set, okay, if we take the set of all of the distinct equivalence classes, that will define a partition. So that will be, okay, a set of non-empty subsets. They'll all be disjoint, right? We just proved that. Okay, if we take two of those equivalence classes, our intersection will always be the empty set, so they'll be disjoint. And when we put them all together, the union will get the whole set. Okay, so here, if two elements are related, they'll be in the same equivalence class. If they're not related, they'll be in different equivalence classes. We're never going to have any overlap. Okay, and everything will be in at least one equivalence class, because everything is at least equivalent to itself. Okay. So let's think about the set of the elements of the power set of the set 1, 2, 3. Okay, and the relation will be that two subsets in that power set are related if their cardinalities are the same. Okay. first of all, let's list out A so we can think about it. I might put it up here so that we have enough room. Okay. So all the subsets of the power set. We know that the empty set is always in there. That one's in there. Okay. That's the only set of size 0. Then we have sets of size 1. So we should have this one, this one, this one. That should be all the sets of size 1. Then we have sets that are size 2. So we have the 0, 1. We've got 0, 2. We've got 1, 2. That should be all the sets of size 2, and then we've got the whole set itself. That's the only set of size 3. We're expecting to have 2 to the third, or 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. I did a good job. Okay. Okay, so there's 8 elements in the set A, and we need to figure out how it's going to partition them. Okay, so well, let's look at the empty set. Okay. That is going to have an equivalence class. So let's think about all the things that would be in that set. Okay. Well, clearly the empty set is related to itself. It has the same, okay, things are related if they have the same cardinality. And every set has the same cardinality as itself. The empty set is no different. Okay, are there any other subsets in here that have the same cardinality as the empty set? No, that's the only one. Okay, so that'll do it for that one. Okay, so let's go on to the next element because that hasn't been covered yet. Okay, the set containing 0. Let's think about its equivalence class. Okay, well, the set containing 0 would be in that one. Okay, because it has the same cardinality as itself. What are there any other subsets that have the same cardinality as it? Sure, yeah, so this one and this one, they both have just one element. So those ones would be in there. But these ones have cardinality of 2, this one has cardinality of 3, they're not in this one. All right, so okay, so now that all of 3 of these, they're in some kind of we've already put them in a set, so we don't need to consider them. Let's go on to this one. 0, 1. Okay, so how many things are going to be in that set? 3 of them. All these ones that have size 2, a cardinality of 2. So 0, 1 is in there, 0, 2 is in there, and 1, 2 is in there. Okay. And then the last one that we haven't considered yet is the 0, 1, 2. That's got a cardinality of 3. Okay, of course it's got the same cardinality as itself. Okay, but that's the only one. Okay. So we would say, if we wanted to call we would call it P, partition P. So partition P. Okay, a partition of a set is a set of non-empty subsets. So I'm going to have to make a set. Okay. And in that set, I'm going to put non-empty subsets. What I'm going to put in there is this, 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 and this. So notice the notation. Okay, that is a non-empty subset of set. This is equivalent to this, right? So this is a set. It's a set containing the empty set. Okay. The next thing I'm going to put in there is this one. That is also a set. This is a set that contains 3 elements. The set that contains 0, the set that contains 1, the set that contains 2. The next thing in my partition is this 0, 1. Okay. Notice these are very important brackets here because this means it's an equivalence class, which means it's a set that contains 1, 2, 3 elements. All of those elements are sets. And the last item that's in there is that set. Okay. So notice, this is a set that contains a non-empty subset, okay, of the elements of A. Yes. Okay, so if we go, let's verify that this is indeed a partition, okay, of the set A. So here's the set A. Oh, we can almost see them both. I wish that it didn't have this little recording thing here. Can that go away? No. No, sorry. I don't know how to make that disappear. Okay, so hopefully we either get it ruined by the visualizer bar at the top, or we get it ruined by the little recording thing at the bottom. All right, so do we have all non-empty subsets? Okay, just looking at here, it might be like, oh wait, is that a non-empty subset? But if we go look, yes, this is a non-empty subset. What's the cardinality of that set? One. There's one thing. Remember, the set containing the empty set, there's one thing in that set. That one thing is the empty set. Okay, the empty set has a cardinality of 0, but the set containing the empty set has a cardinality of 1. Okay, there is something in that set, so that is non-empty. Okay, that's the trickiest one. That's non-empty. This one has 3 things. This one has 3 things. This has 1 thing. They're all non-empty. Okay, so we've definitely got they're all non-empty. Okay, are all of them subsets? Okay, well, this is in there, that, right? If I go look, yeah, all of these things contain only elements from there. Okay, so they're all subsets of the original set. So they're non-empty subsets. Are they pairwise disjoint? Okay, well, if I look at them, okay, clearly none of these are in there. We only put things with size 2 in here. We only put things with size 1 in there. Like, they're clearly disjoint. There's no overlap. Okay. And would the union be A? If I put all of these together, would I get A? Well, there's 1, 2, 3, 4, 5, 6, 7, 8 things. When I put these together, and 1, 2, 3, 4, 5, 6, 7, 8 things up there, right? Yes, I get A. I will get, indeed, okay, it is indeed a partition. Okay. And that will always be true. If we take the equivalence classes, they will always create a partition of whatever set that we're looking at. Okay. One last example. Okay. We have a set S that is, okay, the concatenation of 4 things from the set 0 and 1. So these are bit strings of length 4. So you can imagine what they are. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, etc. Okay. How many things are in this set? What would be the cardinality of S? How many bit strings of length 4 would there be? Somebody whispered it. What is it? You guys haven't had enough binary stuff in your lives to just know this off the top of your head. 16. Yes. 16. Like you got 1, 2, 3, 4 slots, right? You can put 0 or 1 there, so there's 2 choices for that spot. You can put 0 or 1 there, there's 2 choices for that spot. 2 choices for that spot, 2 choices for that spot. So that's 2, 4, 8, 16. Like you just multiply these all together. That's 16 total. Okay, permutations of these bits, right? All right. All right, so yes, there's 16 different strings in here. All right, so we're going to define a relation that A and B are related if I could create or get A, okay, by reordering the bits from B. So, for example, let's look at some examples. So, would 0, 1, 0, 0, is that related to, okay, let's say 0, 0, 1, 1. Okay, can I take the bits in this one, move them around some way, and turn it into this string? No. And obviously, how can we look at that and quickly say no? That would be impossible. Yeah, this one has 2 1s and this one has 1 1. There's no way that I could reorder these and somehow turn 2 1s into 1 1. So these ones are not related. Okay, but is 0 1 0 0 related to 0 0 0 1? Well, yeah, because this one only has 1 1, so I know there's some way I could reorder them. Okay, I could just change it so that this one came second and these ones came last, and I turned it into that one. So these ones are related. Okay, So you can see we can quickly just look at two things and see if they're related simply by either counting the zeros or counting the ones. Counting the ones is usually a little bit easier. But if this one has 1, 1, and this one has 1, 1, clearly I can reorder this one and turn it into that. Okay. So we want to do two things. We want to show that this relation is an equivalence relation. And then after we've convinced ourselves that it's an equivalence relation, then we're going to find the partitions, okay, of our set S. So first of all, we'll show that it's an equivalence relation. Okay, an equivalence relation has three properties. What are they? Reflexive, symmetric, transitive. Good. Okay, so let's consider reflexive. Okay. Would it be true that for all strings in the set S, that S would be related to itself? Could I take S and order it or reorder it in some way to turn it into S? Yes, using the do nothing reordering. Yeah, right? So, okay. S can be obtained from S by doing nothing. Okay, so clearly it's reflexive. Okay. And then we next need to check and see if it's symmetric. Okay. So would it be true that if, okay, X was related to Y, then Y would be related to X? So if I can obtain X from Y, would it be true that I could obtain Y from X? So if I can reorder Y to obtain X, how could I do something to X to obtain Y? Yeah, what would you do, Josh?
Switch.
Yeah, just like reverse what you did for this one. Okay, so then I can obtain, okay, X from Y by reversing the ordering. Okay, so it's definitely symmetric. And the last thing we need to figure out is transitive. Okay, so transitive says that if X is related to Y and Y is related to X, then X is related to Z. Okay, so if I can get Y by reordering X, and I can get Z by reordering Y, would it be true that I could get Z by reordering X? Sure, just take X, reorder it, turn it into Y, and then use whatever ordering you had there, turn it into Z, and now I've reordered X into Z. Okay. Yes. Use I'll say both the reorderings for X to Y and Y to Z to obtain X to Z. Okay. So it's definitely transitive. All right, so it's reflexive, it's symmetric, it's transitive, definitely an equivalence relation, which means it has equivalence classes. Now we just have to figure out what the equivalence classes are. Okay, and we said that what we could do is just think about like the number of ones that were in there. Okay, I think that's the easiest way to think about it. So the least number of ones that you could have in any 4-bit string is 0. So let's start with 0, 0, 0, 0. That's a 4-bit string. Okay, so if I look at the set that's there, clearly it's related to itself. We always have the reflexive property. Are there any other 4-bit strings related to it? No, that's the only one with no no ones in it. So that's the only one in that class, but it's still a non-empty subset. Okay. And then who knows what the first string comes to mind. For me, it's this one with 1, 1. Okay. Yeah, so I imagine you'd either want to put it all the way at the right or all the way at the left. Okay, so we have that one where it's in the, least significant bit spot, where you could move it over here, or you could move it here, or you could move it to the most significant bit. Okay. So like these can all be reordered to turn into each other. Okay. But those are the only ones that have only 1 1 in them. Okay. So that's going to be the end of that class. Okay. Then I might want to think about ones that have 2 1s. So that's the first one that comes to mind for me. Okay. And then you probably need to methodically go through and figure out, okay, how can you get all of the strings with 2 1s in them? I don't know, there's lots of ways that you might go through there. For me, I might say, okay, well, here, let me take this one and move it into that spot. Okay. And then let me take it and move it into that spot. Okay. So that exhausts all the ones where I have a 1 in that first spot. Now let me take this pair and move them into the middle. Okay. And then I could move that one to the front. Okay. So that kind of exhausts all the ones that were generated from the ones being in the middle. Now let's take those 2 and move them to the front. Okay. And once I'm there, there's nothing else I can do. Maybe you think of it a different way. You can count in binary and come up with all the ones that are 2, or look at the distance between the ones. I don't know. There's lots of different ways to do it. Okay. But that should give us all the ones that have 2 1s. Let's look at 3 1s. Okay. So clearly we're going to have that in there. If we follow that same, thinking, we could move this 1 to the front and do 1 0 1 1. We could move 2 1s to the front, do 1 1 0 1. Or we could move all 3 of the 1s to the front and do that. That should take care of all of those ones. And then the last one would have 4 1s in it. There's only 1 of those. Okay, we said there should be 16 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, it does seem like we've covered them all. Okay, and so clearly this should be a partition. Okay, they're all non-empty. They're all disjoint. I never listed any of them twice. When I put them all together, I get the set S, all 16 of the 4-bit bit strings. So the partition would be the set that is the equivalence class of no 1s, of 1 1, of 2 1s, of 3 1s, and of 4 1s. Okay. So if you think of them in a logical way, rather than, what does this equivalence class mean, it's easier to understand. Okay. So that is equivalence relations, and that is the end. So, on our exam next week, we essentially have functions and relations. Okay. So there's all sorts of things that we know about, that need to know about functions. Things like, what is the domain? What's the target? How are target and range different from each other? Okay. You've probably mostly used the word range in your past. Target is a kind of a new concept, so just make sure that you understand the difference between target and range, since that's kind of new. Okay. And then we have all these things, like what does it mean for a function to be 1 to 1? What does it mean to be onto? Okay. What is special when we have a function that's both 1 to 1 and onto? Hooray, if it's 1 to 1 and onto, then we can invert it. And we can find an inverse. So how do you find the inverse of a function? Okay. So you have all those kinds of things. We have composition of functions. Not every two functions that you pick can be composed. Okay. If they're all in a single set, then they can be. Like probably most of the functions you've ever considered up to this point have been like just on the real numbers. And they all have the same domain of real numbers crossed with real numbers, so there was nothing. So you thought that every two functions could be composed. But if we're defining them on different sets, you have to look and be very, very careful that, if you're going to compose two functions, that the inputs of this one produce outputs, and the outputs of that one have to go into this other function. And so you have to have the target of this set has to match up with the domain of this function in order for you to be able to compose it. So just review that. Okay, and we talked about identity functions. So identity functions are things that just map elements to themselves. Okay, and you get this tricky thing where when you compose functions and you have f of g or g of f, you can get different identity functions because the input set and the output sets are different based on the order in which you compose functions. Okay, excellent, excellent kind of test question. So look at examples of those. Okay. What else? I think that was most of what we did with functions. Okay. Yes?
Are you going to make a study guide?
I posted it on Tuesday. Yeah. So yeah, look on iLearn. I posted a study guide on Tuesday. So look at that. Okay. In fact, maybe we can just pull that up right now if you want to look at that.